Hello, Grade 12s. This is our 5th lesson in our series on work, energy, and power. And in this lesson, we're going to focus on the work energy theorem. Now, at the beginning of every lesson, we usually do the homework problem of the previous lesson. But in the previous lesson, I just asked you to revise the theory, which have been done in that lesson. So I'm not going to do that again. But I do urge you, if you have not looked at the work being done by gravitational force on an incline, do go and sit down and see if you can figure out that theory on your own, especially the use of trigonometry. And if you struggle with those identities, do a revision on that and make that knowledge your own. It's really going to benefit you in the exam. Okay, so let's continue with the work energy theorem. What does the work energy theorem say? The net work, or the total work done on an object, is equal to the change of the object's kinetic energy. I think if we do that in symbols, it will be easier for you to understand. The net work done, W net, is equal to the change in the object's kinetic energy. Now we've worked on change in momentum, and by this time we know that change means the final value minus the initial value. So as far as the kinetic energy is concerned, it means the amount of work done by an object is going to be equal to that object's final kinetic energy minus its initial kinetic energy. I can write this equation in a different way, and I can state this theorem in a different way as well. The work done on an object by the resultant force is equal to the change of the object's kinetic energy. So if I write that in an equation, you know that the amount of work done is given by the resultant force times the distance over which this object travels, cos of the angle between them. And then my formula for calculating kinetic energy is 1/2 times mass times the velocity squared. So the change in kinetic energy will be 1/2 times mass times the final velocity squared minus 1/2 times mass times the initial velocity squared. So let's see how we apply this in an example. A block with a mass of 6 kg and a velocity of 5 meters per second traveled down a slope of 12 meters with an incline of 36 degrees. It reaches the bottom of the slope with a velocity of 8 meters per second. Calculate the work done by the object's frictional force. So let's use the work energy theorem to solve this problem. So we know the netto amount of work done is going to be equal to the change in kinetic energy. And in this case, we do have the final as well as the initial velocity. So we can add in some values, but before we do that, we know the net work done is equal to the sum of the work done by all the different forces acting on the object. So let's just quickly identify all the forces acting on this object. Well, there's no applied force going downhill. It's only the gravitational force, the frictional force, as well as the normal force. So we know that work done by each of these will equal to the change in kinetic energy. But now we also know that the amount of work done by the normal force is going to be 0. Why again? Because this object is traveling downhill, so the angle between the normal force and the direction that it is traveling is 90 degrees, and cos of 90, if I fill this into my work equation, is 0. Remember, my work equation is W equals F delta X cos theta, where theta is the angle between F and the direction that it travels. So I know the work done by the normal force is 0. So now let's have a look at the work done by the gravitational force. Well, the angle between the force and the direction that this force is traveling is given by this green angle here. And if I look at this red triangle that I just draw there, this is not really a triangle that exists, but this triangle is going to help me to do the size of this angle. Why? Because this side going down is going to be exactly parallel to my gravitational force. So the angle between my gravitational force and my incline will be the same as this angle of this imaginary triangle that I'm drawing. I know the gravitational force is vertical and the ground is horizontal, so I know this angle is 90 degrees. I know the angle between the incline and the horizontal is 36. So therefore I know that what this angle should be. How do I know that? Because the three angles of a triangle is equal to 36 degrees. So 108, not equal to 36. What am I saying? The three angles of a triangle is equal to 180 degrees. Sorry, guys. Okay, so 180 minus 90 is 90, minus 36 is going to give me 54 degrees. So I know this angle over here is going to be equal to 54 degrees. So now I can fill in all this information with my gravitational force. What is the size of my gravitational force? Is my mass times gravitational acceleration times the distance that this one is traveling, cos of 54 degrees. Remember, I can calculate the work done with the gravitational force if I have the height, but I don't have the height now. So now I need to calculate the work done by the gravitational force using this distance that I do have. If I had the height, I could just write it in like that. Okay. Right, so I fill in my value for my final velocity, which is 8, and my initial velocity, which is 5. If I calculate all these values, then I get my work done by gravitational force. This entire big thing is equal to 414.74. It might be worthwhile to just pause this video for a moment and check on your calculator. And if I take these two energies, kinetic energies, and subtract them, I get a value of 117. So I calculate the work done by frictional force is negative 297 or 297.74 joules. Does the negative number for work make sense? Yes, because my frictional force is acting in this direction and the object is moving in that direction. So the angle between the direction that the object is moving and the force that's acting is more than 90 degrees. So I expect my net force to be, or my work done to be negative. Let's look at another example. A load of mass 75 kilograms is initially at rest on the ground. So this thing is standing there. It is then pulled vertically upwards by a constant acceleration of 0.65. So this is how much it's going faster. It's not its final velocity. By a meter of a light inextensible rope. Refer to this diagram. Ignore air resistance, rotational effects, and the mass of the rope. Use the work energy theorem to calculate the speed of the load when it's at a height of 12 meters. Okay, so let's look at this. What do we know? Our initial velocity when it was on the ground is 0. And we need to calculate the speed of the load when it's over here. So how do we go about that? Let's first write down our equation for our work energy theorem. The resultant force times the distance over which this is traveling times cos of the angle between them is going to be equal to the final kinetic energy minus its initial kinetic energy. So which of these values do we have? Let's start with the resultant force. Do we have the resultant force acting on this mass? No, but we do have the resultant acceleration. And if we use Newton's second law, we can say that the resultant force acting is going to be equal to the mass of this object times the resultant acceleration. So there I've calculated the resultant force acting on this object. Remember, according to Newton's second law, my resultant force is in the same direction as my resultant acceleration. So I know my resultant force is going upwards. I'm also traveling in the direction upwards. So let's see, I've got this value. I know now what my resultant force is, 48.75 Newton. Delta x, I know the distance that I traveled was 12 meters. I know the angle between the force. Remember, my resultant force is going upwards because I'm not working with my gravitational force, I'm working with my resultant force. Because my resultant acceleration is going upwards, I know my resultant force is going upwards. So the angle between those is going to be between the angle between the direction that this is moving and the resultant force is 0. And then I can put in for my values for my kinetic energy. I don't know what my final kinetic energy is. This is the one that I need to calculate. But I do know my initial kinetic energy is 0. So I've got all the values and I can calculate this on my calculator to find the value of final velocity. So if I do my calculation, I get that my final velocity is 3,95 meters per second. Let's look at one more example. A block with a mass of 2 kilograms moved from B up a rough incline to C. When it reaches point C, its velocity is 2 meters per second. Point C is 0.5 meters above the ground. Great. Another example where I don't have the angle, but I do have the height. So let's calculate the work done by the gravitational force. The direction of motion is going up the hill. So we know our block is moving up the hill. So the angle between the gravitational force and the direction of motion will be greater than 90 degrees as shown here. So we expect that our work done should be a negative number. So we know the work done by the gravitational force is given by negative mass times gravitational acceleration times height. We fill in the values, we get the total as minus 9,8 joule. 4.2. Calculate the work energy, or use the work energy theorem to calculate the work done by the frictional force acting on the block. My equation, the net work done is equal to the change in kinetic energy. We know what the velocity is at the bottom of the slope, which is our initial velocity, and we know what the velocity is at the top of the block, which is our final velocity, so we can put in those values. But before we continue, we need to know what forces are acting on this block. So we know it's gravitational force. We know the friction force is acting in this direction. Remember, motion is going up the block, up the incline. So our gravitational force is always in the opposite direction to motion. And then we have a normal force. Now, nothing is dragging or pushing this block up the slope, so we have no applied force acting. So those are our three forces. So the work done by each of these forces, the sum of all of that will give us total work done. We've calculated the work done by the gravitational force already. The work done by the frictional force is what we're looking for, and we know the work done by the normal force is 0 because the normal force and the direction in which this block is moving is 90 degrees, and cos of 90 degrees is equal to 0. We filled in our final velocity as 2 meters per second, as they told us, our initial velocity as 4.95, and our mass for the block as 2 kilograms. So when we calculate this, you can see that all the values is known except for the work done by the frictional force. So then I calculate the work done by the frictional force will be negative 10.70 joules. Does this make sense? Yes, it does, because this block is moving up the incline. So the angle between the friction force and the direction of motion is 180 degrees. So I know it's more than 90 degrees. So my work done will be a negative number. Why don't you try this problem on your own? The simplified diagram below shows a slide PQ in a playground. The slide is 3 meters long and 1,5 meters high. A girl with a mass of 22 kilograms is at the top of the slide at P. The girl accelerates uniform from rest, and she experiences a constant friction force of 1.9 Newton. Use the work energy theorem to calculate the speed at which the girl reaches the bottom of the slide. I hope you find this nice and easy. But remember, it's important that you work out this problem on your own and then look at the next video for the solution. Good luck.